Recall that the definite integral, when we first defined it, we defined it using the Riemann sum, the limit when n goes to infinity of a Riemann sum. We required that f has to be continuous, and then over a specific integral, we said, well, it could be discontinuous, but the type of discontinuity should be a jump discontinuity, and it can have as much as a finite number of jump discontinuities, so we can split the integral over these small intervals and then integrate, and we integrate using the fundamental theorem of calculus part 2. So first we were finding the sum, and then we take the limit, and also we can calculate the area if the shape is nice, like if it's a triangle, or if it's a half of a circle, or if it's a rectangle. And then we use the fundamental theorem of calculus to be able to use the antiderivative to compute these definite integrals. Okay, so the continuity was a necessary condition, and we were computing this over a closed interval. So let's consider the following problem. We want to find the integral of 1 over x squared from -1 to 1. So when you look at this, it may seem easy, simple. You just use the power rule. The antiderivative of x to the power -2 is negative x to the power -1. Plug everything in, and you get -2. Well, unfortunately, this is not correct. This is wrong. Well, here's the reason why this is wrong. Let's look at the graph of 1 over x squared, which you can see here, and we are looking at the area between -1 and 1. Well, this area doesn't seem like it's equal to -2 first, okay, because it's positive, and this should be positive as well, so it cannot be negative since it's above the x-axis. Moreover, the area seems to be, well, it's going to infinity because it's not bounded. That's going to keep going. So the problem is that f of x equal 1 over x squared is not continuous. And the type of discontinuity here, and that's the important part, is an infinite discontinuity. Because when you take the limit of 1 over x squared, when x approaches 0, 0 plus, or 0 minus, you get infinity. So we call this that the function f has an infinite discontinuity at 0. And in this case, we cannot apply the fundamental theorem of calculus. And for this reason, the indefinite integral that we just did is wrong. And if you look back at all the examples that we have done, in all the cases, the indefinite integral, we were finding the definite integral of a continuous function, or a function with jump, a finitely many jump discontinuities. So here we will talk about two types of problems. A type when the interval AB contains an infinite discontinuity, and this is going to be, we're going to call it type 2 integral, improper integral of type 2. And the first type that we will talk about in this video is when you are integrating from a to infinity, so when one of the limits or both are infinity. So here we're talking about an area, an unbounded area, but sometimes this unbounded area may not be infinity, as we will see. Okay, now in either case, so if you are integrating, if you are doing the integral, for example, from a to infinity, let's say of some function f of x dx, or from -infinity to b, or from -infinity to infinity, these type of integrals are called improper integrals of type 1. And if you are doing something like this from a to b of some f of x dx, where this is not continuous, so this has an infinite discontinuity, but not everywhere. I mean, we care about the infinite discontinuity inside AB. okay, or NAB. It could be at A, it could be at B. So in this case, we call it an improper integral of type 2. So this is how we will be calculating these improper integrals. We will make use of the fundamental theorem of calculus part 2, but we have to be careful. We have to use limits as well. So let's take a look at the first definition here. We're saying that if f of x is continuous on the interval a to infinity, we define the improper integral to be the limit when r goes to infinity from a to r of f of x dx. Now, this integral by itself, here f is continuous on the interval ar. So r here is a variable, and r is gonna approach infinity. So we cannot compute the antiderivative at an infinite interval. It should be, I mean, the definite integral must be computed over some closed interval, and AR is the closed interval here. Now, when you let R goes to infinity, so after you compute this, take the limit when R goes to infinity, that's gonna give you the integral from from a to infinity of f of x dx. The same idea, will be true for the integral from negative infinity to b. Now, if you compute such integral, and if the limit exists, then we say that the integral converges. And when we compute the limit, and if it's equal to plus minus infinity or does not exist. When we say does not exist, that means when you have two answers, that means when you have when it does not approach a single value, like for example, limit of x of sine x when x goes to infinity, this is undefined. So that's something that you should know from calculus 1. Now, if the limit does not exist, or if the limit is plus or minus infinity, we say that it's diverse, or it's divergent. The integral diverges. So graphically, this really means the following. What we are doing here is we are asked to find the integral from a to infinity of f of x dx. So basically, this is an infinite area. Okay. So what we do is we compute the integral from a to r, where r is some variable, and then our answer will be in terms of r. We let r goes to infinity. This is gonna cover all this area. Okay, and then we compute the limit. If the limit exists, then we're gonna say it's convergent. If the limit is plus or minus infinity, then we're gonna say or does not exist, we will say it's not convergent, which means divergent. One more case here before we do some examples. We may have an integral from negative infinity to infinity. Okay, in this case, you pick any number between negative infinity to infinity, let's say any number a, and then you find the improper integral from negative infinity to a f of x dx, and integral from a to infinity of f of x dx. If both are convergent, so here you have to be careful, if both integrals are convergent, then the integral from negative infinity to infinity would be the sum of these two improper integrals. If one of them is not convergent, then the whole integral is not convergent. Again, the choice of a is arbitrary. Most of the times we choose 0, but again, it's up to you. A could be any number between negative infinity to infinity. Let us consider the following example. I want to find the integral from 1 to infinity of 1 over x dx. I want to determine whether it's convergent or divergent. To do this, I have to find the integral. So I start by the definition that we had, integral from 1 to infinity of 1 over x dx. This is the limit when r approaches infinity of the integral from 1 to r of 1 over x dx. That's how we defined that limit. Now here, I can apply the fundamental theorem of calculus part 2. Remember that the function, the graph looks like this. This is 1 over x. Okay, and I'm integrating from 1, so this is 1, 1, to r, this is r, so I'm finding this, which is finite over a closed interval. So for this area, I can use the fundamental theorem of calculus part 2. My answer is going to be in terms of r. I will let r go to infinity, and then we will decide based on the value of the limit. So that's equal to the limit when r approaches infinity. The integral of 1 over x is ln of absolute value of x between 1 and r. So this is limit when r approaches infinity, ln of absolute value of r minus ln of absolute value of 1, which is the limit when r approaches infinity. Ln of r, I can just ln of r. Ln of 1 is equal to 0. Now, the limit of ln of absolute value of r, or if you can drop the absolute value since r is positive as it's approaching infinity, then that's going to be of the form ln of infinity, which is infinity. So this means what? That the integral or the improper integral is divergent.